and welcome to another EnergyTech Essentials session from the Net Zero Technology Centre. Thanks for tuning in on this one. Today we're going to be focusing all around how you engineer your technology from lab to market, and we're delighted to be joined by another one of our amazing TechX partners from Astrimar. We've got Caroline and Dan here with us today. Caroline, you've been with TechX right from the start, from cohort 1, is that right?
Yeah, absolutely. Got stuck in there. Passionate about technology, so was keen to get involved and help.
Thank you. And Dan, you were involved in the most recent cohort and a few others as well, haven't you? So what do you do at Astrimar from your side, Dan?
Yeah, I'm one of the engineers at Astrimar, one of the mechanical guys, and just look after general product development, more on the engineering development side, but I try and help out with the reliability and technical qualification as well.
Amazing. Well, thank you both so much for joining us. And I'm sure we'll hear more about what you do in a second. And for those who are watching, whether you're a startup who's been through their TechX program and is still working through developing your technology, or maybe you're a startup thinking of applying or building an energy technology business, these EnergyTech Essential sessions hopefully give you a little snapshot into some of the challenges that startups face. And hopefully our partners can help solve some of those problems and explore them. So today is all about building engineering technologies from lab to market, working through those TRL stages. So I'm going to hand you over to Caroline and Dan, who are going to introduce a little bit about their experience and tell them, I think the question that we posed to you was, if you were an energy tech startup trying to launch your first business, how would you take those first leaps, maybe from TRL2 onwards? So I'll hand over to yourselves to give us a bit of an introduction for the session.
Thank you so much. Great. Okay. So yeah, we've just put together a few slides just to walk through an example journey that we've been on for one of the technology solutions that we've provided to one of our clients. And just thought we'd go through that and talk about how we kind of addressed each TRL technology readiness level as part of that journey. Dan, do you want to introduce the project, the technology that we developed?
Essentially, it's a life of field extension piece of equipment that's designed to reduce the impact for the operators or the field operator, in that it allows them to continue without having to pull and refurb an entire subsea Christmas tree, which is extremely expensive and time consuming. So the solution allowed them to completely avoid that and allow them to maintain operations and have the oil and the money flowing for them.
Cool. So let's go into each of the individual TRLs just very quickly. There we go.
Yeah.
So TRL2 is where we're going to start. TRL1 is just about having the idea and doing initial R&D. So because we were introduced with a challenge from our client, then we basically had that concept or the idea to then build a concept from. So TRL2 is all about developing that concept, being clear of how that concept is going to be used, and then working through some initial kind of designs of how the concept would deliver the solution.
Yeah. So for this piece of kit, we've got a bit of a tongue-in-cheek, literal back of the envelope kind of concept there, but it comes from that. At the end of TRL2, you probably have more detailed drawings, but you're able to do some more feasibility type things. For this, it was calculations, physical clash check because of the environment that it was going into. And then that allows you to then progress and make sure that you can actually physically manufacture what your initial design and your concept is. Essentially, that is what you come out with at this stage, is sort of some basic drawings and some basic clarity of being able to actually complete this design.
Yeah. So on the sides of this slide, there's also some questions there which we use with the technology developers that we support to help kind of frame what sort of things you would address at that TRL and think about the type of activities that you would need to cover. So for the next TRL3, it's about starting to prove that the concept can do what it needs to do and that you're on the right lines. So you'd start to look at some initial analysis or maybe some experimentation or simulation to demonstrate how that technology will deliver the functions that it needs to.
Yeah, so for this technology specifically, we sort of, every stage you get into more and more detail. So we took our initial drawings and concepts, created models. We then carried out some basic FEA, finite element analysis on those to make sure that our concept was sound and that we weren't going to have issues later down the line for the actual conditions that it was going to be seeing when it went into use. That also allows us to do sort of fit, form, and function to make sure that everything's going to do what it's supposed to in terms of its physical envelopes as well. And it's a general just progression of the TRL2 in terms of more detail, which is a general theme. More detail every sort of step that you go through.
Great. When you get to TRL4, then it's about starting to validate the technology in a confined environment. And that might mean doing some laboratory type testing, might mean doing some small scale testing or some simulation. But it's also where you start to look at the risks associated with the technology, and understanding those risks is one of the things that then starts to pave the way into what kind of further testing and analysis is going to be needed to support the qualification demonstration.
Yeah, and for this one, carrying out the failure modes, effects, and criticality analysis with Amica was really important, because what that allowed was our sort of first iteration design. It allowed us to dive into a lot of detail of what the failure modes potentially were of each aspect and each component, how that affects the operation of that and what we're trying to achieve as well. And as Gary said, that then drives the qualification program that we would have on sort of a first article build or a qualification or a prototype of that system. And it allows us to ensure that what we're designing is going to function correctly, as well as be reliable over its lifetime as well.
So then we move on to TRL5, which is about then transferring that demonstration from kind of the simulated or small scale or safe lab environment and starting to look at it into the environment that it will end up functioning in the longer term. So quite often for energy technologies, and you're starting to think about whether it's going to be operating at pressure, if it's working on the seabed, or whether it's going to be working in a seawater environment, or seeing particular chemicals, hydrocarbons, or other technologies. We'll be looking at other chemicals as well, but understanding how it's going to function in that kind of environment.
Mm-hmm. Yeah, for this, it's things like, because it is in a subsea environment, we're doing things like hydrostatic testing, internal pressure testing against what it's going to be seeing in operation, as well as multiple functions of the tool. If it was a coupling, you may engage and disengage a set number of times to make sure that you're happy with the reliability level of it. And that's sort of where we're at here now. We're using those prototype pieces of equipment and just sort of stepping stage by stage into more and more detail, and then confirming what you've been doing in your calculations and your analysis.
Then in TRL6, this is where you're starting to demonstrate at a large scale prototype level, much more kind of reflective of what the ultimate technology is going to look like, starting to integrate subsystems together, and think about actual sort of the final size and scale of the technology that's going to be deployed.
Yeah, so you've proven that it's going to do what it's going to do, that it's going to last the amount of time that it's required to last. And here you're making sure that everything functions within any performance criteria as well, as just being able to survive, and then trying to pull as much data from that as you physically can. As an example there, we've got sort of open and closure times again for probably more of a hydraulic kind of thing. And then more of a electronics side of things would be like data transfer integrity or something along those lines, to make sure that you're happy that when it's in use, it's going to do what it's supposed to be doing as well.
I think this is the last one of our little example and story, reaching TRL7, which is basically about demonstrating the technology, or the prototypes of the technology in an operational environment. And that's really where you could think about deploying it in trials or pilots, or where you're doing a wider kind of system testing that then represents the environment that's going to be actually used in.
Mm-hmm. And for our piece of equipment, that would be more of like a site integration test in SIT, where you're actually integrating it into the system as a whole, and you're looking at a little bit wider to make sure that what you're implementing isn't going to impact negatively any aspects of that overall equipment. Because the last thing, especially for this, the last thing you want to do is shut down a tree that was producing and cause your client a headache.
Yeah. Yeah, so that's kind of our little whiz through the TRL process on the back of an example that we've delivered ourselves.
Really interesting to see. It's a lot of years worth of work explained nice and neatly over that journey. So I guess the first theme to explore is clearly the technology readiness level is a powerful tool to be used, but it's also I'm hoping for energy tech companies familiar, but for some people maybe less familiar. So just as a tool, why is the technology readiness level process important? Who would be looking for that? If a startup was to know what their technology readiness level was, why do they need to know that?
So I think it very much mimics the kind of the design evolution process, working through the TRLs. That they were defined originally by NASA, and they represent that kind of scaling process from paper based concepts through lab scale testing, through prototype testing, and finally to the real deployed technology. They represent that there is a growth in confidence, in understanding, and in kind of just level of detail and rigor within the technology design through that process. They represent that there are design decisions that need to be made through that process. And it's better to make some of those decisions early on, rather than having to go back and recycle and you start back at the beginning again. But it's important that those decisions are made based on the best knowledge available. So hence the need for doing kind of lab scale testing and analysis in the early stages. When you're not committing too many funds to it, you're able to kind of investigate at a manageable scale, use that to support your decisions before kind of confirming those elements of the technology design and moving forwards into the next level of scale, if you like. So it helps to manage the cost, it helps to manage the risk, and it gives you a very sort of systematic journey through the design evolution process. Why it's important, as well as just having that as a management structure for the technology evolution, is also a way of defining where you are on that journey, and helping to plan where you need to go and what other steps you need to take to complete the journey, which then gives confidence to potential investors, potential end users, that you are following a systematic process, that they have a consistent measure, that they can see where you've reached on that journey. And also in terms of helping you understand what you need to still do, then that's good for budgeting purposes, for planning, and for, if you're looking for funding rounds or grant funding or whatever it may be, it helps you to kind of scope what that needs to be in a more sort of defined and traceable kind of way to justify that, really.
Yeah, it's really good as an engineer as well, because it's not quite a checklist, but it's getting towards that sort of side of things where, like I was saying, you've got gates that, once you've established all of the criteria set out for a TRL level are complete, you can then check that off and you can say, right, you can go to your clients or you can go to an investor, and we are TRL level 5 for this piece of hardware or this piece of software. And it allows them, like I say, to make the sort of investment decisions and also decisions whether they may or may not use your solution at all.
Yeah. That's really good. And I think a lot of the startups that we see, often the first time they have to look at TRL is in applications for maybe grant funding or accelerator programs. And they have this list of 1 to 9 and they tick a box. Hopefully there's some accuracy behind it. But if you were in those startup shoes, how do you know when you've passed a gate, and how do you decide which, or do you decide, or how do you understand what TRL level you are at any one point in time?
That's a really good question, because I think when you look at the kind of definitions of the TRLs that are out there in the public domain, whether it's the NASA version, original, or evolutions that have come out through different organizations, and NZTC have their own TRL definitions, very much based on NASA, but slightly tweaked for the sort of energy technology that NZTC is dealing with. But they're quite high level descriptions. And I think the challenge is that you can read that description, and that description might be that you've developed a prototype or you've done some lab testing, but it's such a high level definition that it's actually, I think it's really hard to make that judgment with any confidence, because sometimes you may have done some lab testing, but you may not even know all the lab testing that you need to do yet. So does that mean that you've completed your lab testing or not? From our perspective, and maybe this isn't helpful for applications, but from our perspective, you could be at a number of different TRLs all at the same time. You could have started your TRL3 sort of lab test work, and also started doing some small, some kind of early prototyping, for example, on a part of the system. So the answer really, technically, if you're claiming a TRL, you should have completed that TRL. But I think in terms of grant applications or funding applications, it is expected to be a little bit more subjective and a little bit looser interpretation. But I think it is important to think about what you still need to do and not overclaim where you think you're at. I know sometimes it can be tempting to squeeze yourself into a TRL to fit into a certain category of funding. And okay, there's justification for that at times, but you need to be true to yourself and true to the technology. And it's more about being clear on what else you need to do and being honest about that, because the last thing you want to do is claim a higher TRL. And then find that actually there's an awful lot still to be done to prove the concept in those earlier stages, that then almost undermine your explanations leading to that point.
Don't have much. Pretty comprehensive, to be honest. And there are, I guess, there are tools available that would allow you to then make sure that you meet all of those criteria for ticking off. Absolutely. Then you've completed a full TRL level, full TRL package, and then they can also show you that you may have all but one of 4, but you've completed 3, so it can give the people a bit more of a judgment call of how far along I think your technology as well actually is.
Yeah, so I mean, I guess maybe we can plug RAPAT a little bit. We have this Excel-based tool called RAPAT that we've put a TRL assessment worksheet into it, and that's really from our slides where those questions came from, the 5 questions per TRL. That's not available in any kind of general guidance on TRLs, but we've developed it based on some more detailed guidance that's available in within an API recommended practice, API RP17Q, which is for subsea systems qualification. And in there, it does take this kind of more detailed level of, well, what does it mean to reach each of the TRLs? They actually use a 0 to 7 ladder rather than the 1 to 9 ladder that everyone else uses. So there's a little bit of interpretation there. But we've taken that principle and said, okay, what does that actually mean? What are the things you want to be considering at these levels? And that's where we've taken how we've built those questions within RAPAT. So it's informed by industry best practice. And I think it does add that extra level of rigor, but not just rigor, it also adds guidance inherently in the fact, as Dan said already, it becomes almost a tick box checklist to help you think about the range of things that you would be considering at that TRL. But that's very new news to a lot of people, so you may already have applied and put in a subjective estimate on what the TRL is, and that's how most people do it. What we're suggesting is a little bit more rigor helps with the planning and helps with just that the evidence and the justification for where you think you're at as well.
Yeah, I think TRL as a system is really powerful, I think, as a concept, because I know what I'm like when I'm trying to plan things. You know, the idea of climbing a mountain is just so enormous when all the things you need to consider, and it can almost be stalling for engineers and startups to think,
yeah,
there's hundreds of experiments and tests. So maybe let's think about the practicalities. Maybe let's say I'm a university spin out and I've got a TRL3 concept, or I've got an idea of what my technology should be. What are some practical ways that you would actually plan the engineering and development? How do you know all those experiments and things you need to do at each different stage? Is there any best practice or tools or systems or processes that you would use to kind of download, here's all the things that are going to need to happen over the next 3 years, and figure out who does them, when they get done, how they get done? So any practical things that you would advise for startups who are on that journey? They know what they want to build, they just need a plan on how to build it.
Do you want me to go first?
I could try, yeah. Sort of like as we run through those TRL levels, it's very progressive in terms of you start with the concept, you then move on to like sort of feasibility and ensuring that what your great idea, and there are a lot of great ideas out there that just aren't able to be implemented yet. So then you've got your sort of feasibility. You probably want to do some sort of market analysis of it as well, and this is all feeding in. Again, a shameless plug, but from the RapApp tool, it has all of these functions in it that allow you to do these things. So you're doing a lot of background. You're then moving on through in terms of sort of a hardware perspective, which is sort of my bag. You'll be doing your calculations and your initial models and your analysis and things. And as you progress through those, that's sort of your plan. And again, when you get to the stage of having potential prototypes or a final design rather, you then create that FMICA, and from those failure modes, that will drive your test program a lot of the time, because it tells you where you may or may not find that there are issues, and then you want to test to make sure that they can be overcome, and that your product can work reliably. And then as you progress through the TRL level, that's looking at what you require for the next one quite often drives a lot of your planning. You have to have access to an example of TRL, whether it be the NASA 0 to 9 or the API industry 0 to 7, 1 to 9 or 0 to 7. Using those does sort of drive the plans quite a lot of the time. It won't give you step by step, but it will give you what you should be looking to achieve as your next sort of objective.
I think as well as that, there's the qualification process that is defined by some of the certification bodies, particularly in the energy sector, sort of DNV, Lloyd's Register, and Bureau Veritas, as well as the API one as well. They all have this kind of 7-step process called technology qualification. And the idea of technology qualification is particularly for technologies that don't fit into existing codes and standards, which basically is any new technology. The standards can be created if the technology is standard. So any technology that doesn't inherently fit into a standard that you can take off the shelf and say, right, I'm designing this, this connector. I have a connector, there's a standard for connectors, I'm going to design my connector to meet this standard. Well, that works because connectors are a standard product, but you're developing something that's not standard, it won't fit within the existing standards. So the technology qualification process takes you through a journey of that starts with work out what it is your technology needs to do, define the requirements for the technology, define they call it a qualification basis or a requirement specification. And really that's where you're setting the boundaries on what your technology needs to do. And it involves doing market research as part of that. You want to know, what does the market need in terms of your technology? You don't want to be developing something that no one wants. So the sort of understanding the market and also understanding what's achievable for maybe your minimum viable product, that first generation of your technology. You define that at that stage. Then the process then says that you then assess the technology maturity and you do a TRL assessment at that point. You can do that if you want to. I mean, it's not a necessity at that stage, except to identify where the gaps are or to communicate to others where you think you're at. It's a useful kind of milestone assessment. But you could do that at any point along the journey. Then, having defined what it is your technology needs to do, that's when you then do the risk assessment. And Dan mentioned the FAMICA, the failure modes, effects, and criticality analysis. That's one way of doing it. You can do, there are other types of risk assessments that you can do, but you basically then assess your technology against the requirements and say, well, how will it fail to meet those requirements? And for each one of those risks, you then have to say, well, what's my evidence that I am not going to have that issue? So some of those things, you may still be able to take standards off the shelf and say, well, if I design this bit of my technology to that particular standard, then I can have confidence that that bit of my technology is going to work. And so you can still use standards where they are relevant for subsystems and components within your technology. But there'll be other things that don't fit within those any codes and standards, and you have to say, well, okay, well, I need to test it. I need to design a test for that particular function, for that particular risk, that will then demonstrate that it's not going to be an issue. It may be you're going to put something in a corrosive environment and you need to be sure that it's not going to corrode a rate that would then be life limiting on your technology. So you would then do some corrosion testing as an example. And then having done that, you then build your test plan, and some of those tests can be done at small scale testing and will be done in early TRLs, such as corrosion testing, that we've done as part of selecting your materials, and you could do that at a lab scale, and it would keep the cost of that test to a minimum. You wouldn't design your whole technology, build it, fabricate it, and then start testing it for corrosion rates. That would just not make sense. So you look at the tests and you say, okay, where do these fit within the TRLs in terms of the scale that makes sense to get the answers that I need to demonstrate that particular risk is not going to be an issue. And then through that process of doing the testing, there may be analysis and simulation that you can do to minimize the amount of testing that you have to do. You may want to validate your analysis with tests. You might want to extrapolate your tests with analysis. And so you can do a combination of those things to optimize how you allocate your resources, and also not just cost, but also time as well. You can do things a lot quicker through simulation than you can through testing, as long as you're simulating the right things with the right conditions. And then it's the output of all of that then builds your evidence and your assurance. And ultimately, if you're looking for certification, it's that evidence that you would then submit to a certification body. But even so, if you're not looking at certification, you could still give it to an investor, an end user, and say, look, this is the proof that it's going to do what it needs to do. And you can really trust this technology because I've got all this evidence of everything we've done to test every element and every risk and every concern.
Really good comprehensive plan. That I think I've got tons of different areas you could pick in there, because I think where I'm summarizing is, if I was sat with a team of co-founders and we were there with our idea and we were needing to figure out what to do, a few steps you might take would be, of course, your engineering brains figuring out, well, here's all the tests I think we're going to need to do, because I guess the engineers will have a sense of their own, but equally looking at maybe some of these TRL tools that will give them some of that guidance to fill in what I'm picturing as some mega project plan spreadsheet. But then also that really interesting point about the qualification process and possibly some of the risks, because then once you know maybe the standards that you're working to or some of the steps that will be required to get to the point, again, they can all get added. So there's this mega list of tasks that might help them figure out what we do at each TRL. I'm interested in that piece around, especially for EnergyTech, if I'm imagining right at those early stages, physical testing and physical experimentation, just even some of the parts and equipment can be quite expensive. They maybe don't have the lab space. If it's in a space like hydrogen, where actually safety and things could be quite complicated in the early stages. What's the balance in terms of, getting that evidence and engineering data you need of simulations, digital equation modeling versus physical testing? And can you still progress enough with some of the cheaper non-physical methods, or at what point is there really no question that you need a physical test for these? Kind of what's the experience of that, and when should startups start thinking, okay, can we still progress with just digital and research and modeling alone?
Well, as Carrie said there, you'd initially start with the lower cost, faster option, which would be the modeling and the simulation. It really depends on my personal perspective. It really depends on sort of experience levels and things as to how far you take that and how much you're willing to believe the results as well, because it does take an amount of experience to know that what you're seeing is more what you should be expecting, because you can put anything in, you can get anything out. So knowing what you're putting in and then being able to evaluate those results with a bit of experience and a bit of knowledge at the end is very, very important. You can take that to a certain extent. And it really depends on the product and the application and the industry that you're going into as to how far you can take that. If you're building a giant bridge, odds are you don't want to start doing full-scale testing of overloading it and things, in which case you have to really trust that your analysis is good. And you have to have the right people in place to do that. If it's a really small-scale test, a really small piece of equipment that is maybe a little bit cheaper, a little bit easier to manufacture, and you may want to validate your results by then doing a destructive test on it and show that what you've modeled and what you've done in your simulations correlates, then that would be more possible to do. It just depends on the piece of equipment, which is a bit of a wishy-washy way of answering your question, but I think that's basically what you have to come down to, a bit of experience and a bit of application of the technology and what's physically possible. But things like corrosion tests and things are very simple to do, and because you just require a sample rather than a product to do that sort of thing, as well as like material choices in terms of strength and hardness testing and what have you. So there's elements that you can do without having to have a full scale product.
Yeah, I think as well it's down to the complexity of the technology, and both in terms of system complexity, but also in terms of sort of the technical sort of the application of engineering principles and the complexity of that. If you are using known materials in a known way, and there are good engineering models and methods for doing that analysis, then of course that's going to be the simplest and most effective way of doing your early stage development. But if you're using materials in a new way, beyond what is well understood, and you don't have the engineering models there to really confidently predict how the material is going to behave, for example, then you need to do some testing to understand the material behavior before you can start to do the modeling. Otherwise, your models could be completely all wrong. And one example of that is in things like additive manufacture. So where in additive manufacture, you're building the material as part of the manufacturing process. And therefore the material properties are not going to be the standard material properties, especially if you're then looking at composites and things like that. And you only actually generate material properties once you've fabricated or additively manufactured that material sample, and how the shape of the sample, the layup of the additive process can all affect material properties. So for cases like that, there is a limit on what you can do in terms of modeling without having first done some testing on that sample to actually understand how it's going to behave.
Excellent. Okay, so I'm picturing it now. So I can see our big mega task list, and I can see where there is an opportunity to do some of those maybe corrosion testings or materials testings. We can try and do lab scale or a small experiment, or work with partners maybe who have some of that already, through to then, okay, we can do some of the simulations. So I can see how an engineering team might need to divide that up. I guess a broader question related to that. So we've figured out some of the sources of how they'll build this lab to market kind of plan. But there's always things that you don't know. You don't know what you don't know. You've never built this type of technology before. You haven't got experience. So while you've looked at all the certifications, you've looked at TRL, you've brainstormed, you think these are all the experiments and tests I need to do. There'll inevitably be something you haven't thought of yet. Is there any top tips you've got in terms of early stage founders who maybe don't have all that experience? Who do they talk to? Where do they go? Where do they look? Just to kind of get a sense check that, how do you know if you're doing it right? How do you know you haven't missed something? What would you do?
Oh, that's a really good question. I think draw on people that understand the journey and people that can ask the difficult questions. I think quite often we're very good at convincing ourselves that it will work because I thought of it and I've thought of everything and I'm confident. Whereas other people have a different perspective, and having someone devil's advocate almost near you who can ask those difficult questions and say, yes, but have you thought of this? And almost the negative person that you don't actually want to have around. Sometimes they're quite useful. They can ask those difficult questions, but also looking at comparable technologies, looking at what they are doing, how they're achieving what they're doing, thinking about why they do that, and is there something, do they have a feature that you don't have in your technology yet, and is there a reason why they have that? So thinking about how existing kind of solutions provide that can start to raise sort of questions about the things that you maybe haven't thought about.
Yeah, no, I agree. I think working through, again, I'm a shameless plug, but working through some sort of checklist in terms of software or steps that provide you maybe with the questions that you wouldn't have thought of or you wouldn't have asked. Or a lot of reliability and risk analysis being carried out on it may pull up some of those questions as well. And as Carrie said, get the people to ask the awkward questions. As an example, pulling something a bit random, but at a previous place, one of my bosses stopped getting invited to design reviews because he asked the awkward questions. But it was things that were potentially going to cause issues down the line. And in a lot of instances, they did then cause issues down the line because he wasn't invited to things. And you don't want to get to the point where you've created a prototype or you've started to actually try and implement something to find that there's a failure mode or a risk or something that you've missed, because at that point it's so expensive and so time consuming to go back and fix things. You really need the experience and the people and the tools to try and cover as many of those things as possible at a really, really early design stage. Which may or may not answer the question, but it just sort of feeds into trying to get the right people and the right tools and the right questions, like you say, without missing any of the gaps.
And you mentioned there, I'm interested in how, again, my scenario I'm picturing is a relatively early stage startup that's just building up from scratch. They maybe are still in the university, they've got some lab things, they're used to maybe university operating processes and are now building their own out. What are some of the just general engineering design best practice? You mentioned design reviews, you've mentioned some of these risk modes. What are the kind of, is there regular meetings that should be happening? Is there kind of, and I guess my second question, but I'll bring it in now because it might come up, was I was also interested in the document trail that you need in terms of your evidence. So just what is best practice in terms of how do the engineering team operate? How do they keep track of things? How do they share ideas? What, if you were building a startup engineering team from scratch, what would the system look like?
I don't think I've ever come across an engineering team that works the same as another engineering team, to be perfectly honest. Everyone has their own way of doing things, but you just have to make sure that you're systematic, I think, is the biggest thing for me, and make sure that you are doing those. I wouldn't say that there's any standard engineering process for in terms of like design reviews. I think they're just one of those things that is incorporated in the engineering process, and it doesn't have to necessarily, if you didn't know about it, you would be doing that, most likely you'd be doing that anyway, by asking your colleagues about, well, what do you think about this? Does this do what it's supposed to do? Do you see any issues with this? And that's all that the design review is, sort of eking out that what you've generated as maybe a concept is actually fit for purpose. And again, asking the difficult questions. So have you thought about, it's actually going to go an extra 1,000 meters underwater. Is it going to get crushed by the pressure of the water? Just anything like that.
Yeah, I think maybe the sort of practice of system engineering is a useful thing to kind of think about in terms of providing a generic systematic process, because it starts with the high level, what is it the whole technology needs to do? And then it breaks it down into parts of, the subsystems and the components and the parts that are going to deliver that. And not only that, kind of gives you a structure in terms of making sure that you kind of pass down the requirements from the overall system into which parts of which subsystems are going to deliver which of those requirements, and how then they're going to interface with each other, and making sure that the right requirements are allocated to the right parts. But not only does it provide that process, but it also provides maybe a sort of a documentation process for, part numbering, system numbering, labeling, document control, all of those things. If you have that system view, you can start to, ensure that your drawings and talk to each other, your design specifications talk to each other, your reports talk to each other. It gives you a structure to work in, and in doing that system down through the subsystem components and parts, also it gives you that level of rigor, and also helps you to recognize where there are interfaces within the system, so such that that part is going to mate with that part and is going to fit properly, and the functions are going to be transferred from one to the other, and so on. And when you do this system breakdown to the part level, you have to then build it back up again, back up to the system, to demonstrate that the system is still going to do what it needs to do. So whether that's through the design, analysis, or documentation process, you have this kind of structure that drives different parts of the team to kind of talk to each other and make sure that you're still delivering what it is that you need to do.
Yeah, and I think you'd asked about documentation as well, and I think you mentioned having things like qualification basis or qualification plans, but you want to go back to sort of your functional design spec. What do you want the product to do? So there's lots of pieces of documentation that may or may not have an official name when you're doing a sort of startup from university or whatever. But as long as you're outlining probably what you want it to do, what your design is, how you're going to make it do that, and then proving how you're making sure that it's not going to fail. Those are all sort of steps in the documentation ladder, I guess. I'm trying to make sure that you've got everything recorded.
That's good. Anything else in terms of how you then evidence? So you do all your experiments, and I guess you get results and practical, I guess even videos of it doing stuff, or not doing stuff. How do you then what is the best practice in terms of collating that to make sure you do get the regulatory approval? Because the last thing you want is to go through a program of testing. Maybe you've got a prototype, you've tested it in a simulation, and then you go to your qualification body, or you go to a customer and you present something and they say, oh, I can't see this, or I don't know this, or I don't understand these results. And all of a sudden you're going to need to run that program again because we can't sign it off. How do you protect against that risk of, because startups, they're not going to know, they've never done this before. They're not big engineering organizations. They're experimenting. So how do we get the documents right to make sure you don't miss your certification?
I think it's about being systematic. Again, this links back to the technology qualification process, and it also links back to the RAP Act tool that we've created as a way of doing that. It's about demonstrating the links between the story of, this is what the technology needs to do, this is how it could fail to do that, and this is the evidence that it's not going to fail, that it is going to do what it needs to do. And building that story, you ultimately end up with, like you say, a whole ream of different test results and evidence of different formats and things. And what the certification body or investor or whoever is looking for really is kind of proof of rigor. And ultimately for certification, they may go into every I and every T and make sure that each one's been dotted and crossed. And so what we would suggest is that you build up a dossier of evidence, and with technology and just doing things electronically, building up a dossier includes like hyperlinks to where that file is, and so on. This was what the requirement was. This is what the test was to demonstrate that requirement, and this is the link to the evidence that shows it, and then ultimately a conclusion that came from that. For certification, then you may end up with not just this kind of document of links, but you need a story at the front of it. It explains what you did, how you did it, and why, and then it just signposts you to all the different outcomes of all the different tests that you've done. But creating something from the beginning that has structure and a systematic process means that at the end, you have a link in every box and a tick in every box. Then it's that structure that someone else can then pick up that dossier and say, okay, I understand this. I can see the flow of the decisions. I can see the flow of the design and the evidence that's being gained. And they can just choose which ticks to look at, which boxes, which links to click through to, and review and validate that evidence as part of their process.
Yeah, I would say as well, don't do everything on a whim. You do need a plan.
Yeah.
And the more planned and systematic you are, the easier it is to actually go through all of those tests. So in your qualification plan, for example, you'd say to cover all of the potential failure modes we've previously identified, you need to do test 1, 2, 3, 4, 5. For test 1, you'll have your usual kind of thing that a lot of people will have done at university in terms of, what we're trying to achieve. Here's our equipment. Here's how we've carried out the testing. Here's our results. And then you do that for the 2, 3, 4, 5 as well. And that would be able to be collated and then handed to a governing body or a third party to actually sort of evaluate that you've identified what could go wrong and how to mitigate those by testing. And then you've carried out those tests and it's passed and it's achieved what it's supposed to achieve, just as a nice, easy set of steps.
That's really helpful. And to unpick there, that's a really good structure. But I guess one of the challenges, sometimes the tests don't pass and something goes wrong, or the failure mode is validated, and you have test number 2, but you have 2 A, B, C, D, E, F, G, because you have to keep doing it. How do they handle that? And I guess I think there's a culture in startups, maybe not in experimentally, because it's generally kept under wraps, but of always having to look like everything's amazing and our results are fantastic. And, it could be quite a blow, especially imagine an engineering team. You've got a CEO who's been talking to the investors, who's saying, we need the results today. And the engineering team, it didn't work. We need to change the material. It's really a blow to them. How would you as a startup handle that? Not just in terms of redesign of the experiment, but also just as a team, handling that failure when you're so passionately desperate to make it work.
I think it's recognizing that it's an evolution process. Even the technology qualification kind of guidance, that like the DMV guidance, it includes a loop back for modifications. It recognizes that technology development is an evolution process, and something that doesn't work, a test that isn't successful in terms of what its original objectives were, doesn't mean it's not successful in the technology development process, because it's still a learning. And if that means that that technology ends up with a more resilient material or a more robust design, or just a more defined parameters on how it's going to be used, and says, actually, for now, we can't get it to work in this environment, but we know we can get it to work in this environment. So for this generation of our technology, we're going to say just sell it into the environment that we know and can be confident it works in, and we'll worry about the other environment for generation 2. And you just define a limit on how it's going to be used, and that's a good thing as well. So it's all about learning and building confidence. And the more uncertainty you have at the beginning, that reflects into a lack of confidence. So it may be that the path changes, but that path becomes a more confident path, because you've learnt on the journey, and you've removed the things that are not going to work, and be able to hone in on the elements of the technology that will work.
Yeah, I don't have much to add. I mean, from an engineer perspective, it's always disappointing when something doesn't work the way you want it to have to work. But I think that it's sort of part and parcel of generating something novel. You can't always have everything work first time, and I think that sort of understanding comes with a little bit of experience of having done it and sort of failed some of these tests. And on the flip side, it's a bit of a cliched thing to say, but failures lead to experience for the next time. And what you find is, with any luck, those failings teach you going forward to minimize those failures, and you do tend to improve. Even with a novel piece of equipment, there can be carryovers, and you find that you do sort of start to minimize your sort of test failures. But yeah, I think it's just something that comes with experience of not beating yourself up too much if things don't quite go your way.
Yeah, I think failures inform decisions and reduce uncertainty moving forward.
Yeah, and it's better to find it at the test stage than you've delivered it and then it fails as well.
Definitely. So failure part of the process, and I guess maybe startups bearing that in mind in their optimism. And I guess there's in finance, you often have an optimism bias calculation. I imagine the same for engineering, to say, yeah, we think it'll take 6 months, but let's plan for 8 just in case. Or is that common to kind of, how optimistic do you think startups are or engineers are when they're planning things versus the reality?
Probably experience-based again. After you've done it and you've given yourself the wrong time a couple of times, all of a sudden you think, oh, maybe I'll overestimate this. And from a business perspective, sometimes depending on how unknown something is, we'll build in some contingency to cover that exact instance.
It's better to be pessimistic. Give yourself breathing space. Giving yourself a bit of modification and continuous improvement time. And if you don't need it, then you're even more successful because you've done it ahead of schedule. But if you do need it, then you're not causing any big disappointments and frustrations.
I always really like the under promise and over deliver kind of method in terms of give yourself a little bit extra time if you can, as long as somebody's not screaming for something by a certain date. Give yourself a little bit extra time, and if you're overachieving that, then you look better, and then you also know next time how much actual time it takes as well, without having the first time gone over the time or gone over the budget as well.
My next question is, I guess, I don't know if it's a controversy. I'm thinking of some of the engineering advice I've maybe heard startups being given, and I wanted to just get your view on it. So, for example, one of them, and you've touched on this a little bit around, there's 2 elements of it. One, there's this critique of engineers that they over-engineer everything. There's 1,000 features when you only need 1, and there's 1,000 moving parts when that's a huge risk. And then there's also the piece that you brought up in terms of already tried and tested bits of tech. So advice I've heard startups be given is, where you don't need a novel type of screw or a novel type of casing or a novel type of cabling, use the most well-established technology on the market and only focus on your little bit. Yes, you might be able to get that 1% more efficient electrical conduction, or you might be able to get a better shape and size or weight, but actually the thing that's novel is your piece inside. So don't over-engineer the bits you are not unique in. What do you think? Engineers maybe push back on that because they want to make their own thing, but what's your view on that advice?
I completely agree with that. I mean, there's no point in reinventing the wheel just because you can make it 1% more efficient. What I would be, if the whole thing is you've got one piece of novel equipment connected to 5 pieces of equipment you could buy off the shelf, people that have established technology in that area, for your initial iteration of your equipment, I would generally say that you should be using what you can, and then building on that for maybe a next iteration, next generation of your equipment, like you say, try and then start eking out. It may not even be required, but eke out efficiencies or eke out, weight loss or whatever your end goal is, to try and make your product as a whole more inviting to an investor, inviting to a customer. There's no point in taking risks you don't have to take.
Absolutely. I think it helps with the sort of certification of the technology as well. If if you're looking for kind of C compliance type certification or ATEX certification, whatever it might be, any type of certification, the more components that you can use within your system that are already compliant, already, you're buying them off the shelf and they already come with the relevant certifications, then the amount of work that you need to do is far reduced. The risks are far reduced, and the uncertainties and costs are far reduced. As Dan said, I think you can go back and you can make things better later. You can choose to have, generation 2 has this new way of delivering such and such a function. But if you don't need it for your minimum viable product, then I would say don't do it. Focus on what you need to do to get the product ready for use. And I think that also means, I've just lost my train of thought there. I was going to say something really important and it's completely gone. It might come back to me. Let's move on.
Yeah.
No worries. Well, we're on to our final kind of theme here, just as we're about to wrap up, because I think there's a lot of insight and we've kind of explored that journey of a lot of the lab-based, a lot of the testing, a lot of the kind of systems and planning. So the last theme is really, let's say I've got my energy technology, I've done a lot of the lab testing, I've done some, prototype testing. I'm now really in a customer site. So it's maybe the TRL7. I've actually got a field trial partner. I've got my prototype, maybe using some existing components with my piece. I'm not fully certified yet, but I'm out there in the real world and someone's plugging it into their system. What are the kind of, if you were advising me or you were working with the startup, what are the kind of red flags or things that you've seen at that stage, taking the technology into a real live environment? What are the issues or the common things startups miss up, or things that are they under consider? Anything that comes to mind in that we've plugged it into a real customer site, what we haven't done something right, or
I think it's about understanding how it's going to be used by the customer, and making sure, and it may mean revisiting and updating, but going back to your risk assessment and making sure that it is relevant for how the customer is going to use it, and also that the customer understands your expectations for how they're going to use it. So that might mean, clear instructions, training, labeling, protective systems, anything that you need to make sure that you don't have inbuilt assumptions in the technology and how it's going to use that you haven't then checked are valid for how the customer is going to use it, and that they have a good understanding of what your expectations are for how it's going to be used. It may be, even though you're not getting the technology certified, it may be that for safety reasons that you do still need to have third-party checks on some of your safety calculations and or tests before the customer will before either legally or your customer will accept it within their facilities. But I think it's about making sure that you have that roundtable discussion with the customer, that they understand what your expectations of how it's going to be used is, and you understand what their expectations are as well, and any gaps are filled very quickly.
Yeah, I think it comes down to having a really well-defined functional design spec. If you know, between you and your client, you know exactly what the piece of equipment is supposed to be doing. When you come to integrate it and test it in their system, you shouldn't really have any surprises by that point. Like say, you may have third-party verification or witnessing to make sure that it's safe before it's fully applied. But yeah, really, really knuckling down and spending the time to get what everyone wants out of this final piece of equipment nailed down at the early functional design spec stage is really important. That limits your risk when you come to actually putting it on or integrating it into a client's piece of equipment at the end.
Excellent. Well, thank you both so much. That's us at the end of our time for today. We probably could talk for another 5 hours about all different stages of the energy technology journey, but thank you. I think we've got a really good insight of not just what the TRL scale is, why it's important, some of the systems and processes that early stage startups go through, talked about reliability, looking at your kind of risk testing program, how you know what types of tests to do, how you manage the results, how you work with customers. So there's a lot of topics we've covered that I would hope for any of the people who are watching, maybe you've got a startup already, maybe you've been through our program and you're now in that live environment stage, that you've kind of got some refreshers and got some insight from our lovely partners at Astrimar, who have been supportive of the TechX program and the Net Zero Technology Centre for many years. So thank you both for your time. For those who are watching along, this is part of our EnergyTech Essentials from the Net Zero Technology Centre. Our goal is all to help energy technologies accelerate faster, get deployed, and hopefully get commercial so we can get to net zero as best we can. So thanks for your time joining the session. There's lots more resources on our website. We run our TechX Clean Energy Accelerator program that generally opens every single year. So make sure to have a look on our website to find out when the next application window is. Thank you for tuning in and have a fantastic rest of your day.